Good morning, Australia, afternoon, evening, any other part of the world you may be connecting from. Welcome to the 2020 on Dairy Research Foundation Symposium, a very different symposium this year in a very different and challenging year. As we did yesterday, before we begin our symposium, I'd like to acknowledge the traditional owners of Australia and recognize the continuing connection to land, water, and culture. I am currently on the land of the Dharawal people of the Eora Nation and pay my respects to the elders past, present, and emerging. I'd like to also thank again our sponsors and supporters, Local Land Services, our major sponsor, our major media partner, Dairy News as well as the Regional Development Program for Dairy Australia, our own Sydney Institute of Agriculture, which brings together the multidisciplinary research in agriculture across the University of Sydney, and New South Wales Farmers Association, particularly Dairy Committee. I'd also like to thank our organizing committee this year, Tony Burnett, Helen Golder, Michael Parrish, Colin Thompson, Sabrina Lomax, Cameron Clark, Paul Van Well, Nicholas Lyon, Todd Wyman, Emily Nilsson, and last but not least, our own Lynn Garner, who is sitting beside me. And Lynn has been pivotal and outstanding in her work behind the scenes to put together what you saw yesterday and what you're seeing today. So thanks very much, the committee, and thanks very much, Lynn, for your help. Yesterday we saw two of the sessions with the business and focusing on business risk and the society and the problems in relation to social license. Today, we're concentrating a bit more on emerging scientists, what is happening, what science can bring to the table, with Rupert Brookmaier from Switzerland, and also our emerging scientists, what the students are doing in Australia and other parts of the world. And also, with the final session will be on innovation, with focusing particularly with what's happening at the University of Sydney, and also focusing a bit on one of the key inputs for dairy production anywhere in the world, which is energy. So with that, I would like to call Dr. Nicholas Lyons to introduce the first session today. Nicholas is from the New South Wales Department of Primary Industry, so I will leave all of you with him. Nico?
Thank you, Yanni, for that introduction. Good morning, everyone. As Yanni said, my name is Nicholas Lyons. I'm the leader dairy for New South Wales DPI, and I'll be your chair for this first session this morning. I would first like to introduce Professor Rupert Brookmeier. Rupert is a world expert in physiology and endocrinology of lactating ruminants. He's the head of veterinary physiology at the University of Bern in Switzerland. He's done a lot of research into milking physiology, milking management, mammary immune response to pathogens and mastitis. He's written and authored more than 300 articles in scientific publications, and his work has led to improvements in milking management and milking routines. So it's really a pleasure to have Rupert with us this evening for him, given that he's in Europe. So welcome, Rupert, to the stage, and I'll flick presentation rights to you.
Oh. I lost my screen. Good morning. Oops.
In the meantime, I take the opportunity to thank our sponsor for this session, Local Land Services Hunter, and remind everyone that there's a Q&A tab on your panel, so you can send any question for Rupert while he's speaking, and we'll control those. And if you have any technical issue, there's a chat tab that you can also use, and Angus is on the background.
So thank you, Nico. Sorry for the delay. I somehow lost my slide, but I think it's back now, and you can all see them. So today I want to talk about novel research developments in milking management to optimize performance and animal health. So these are my topics today. So there's a lot of technical developments. Also, technical developments are cheaper, getting cheaper in a way. So they allow a lot of precision dairy farming options related to milk harvest. So one of the important points here is that it's very much useful today to have continuous milk flow recording in modern systems, and it's also possible to do automatic analysis of various factors in milk of individual cows. So this leads to a number of options to optimize the milking process, and also to use milking data and milk analysis for surveillance of production parameters and health parameters as well. Let me start with milking machine settings. So traditional milking machine milking is basically performed with just one system vacuum setting, which is used throughout the milking. Cluster detachment traditionally is more or less when milk flow stops. So at a very low detachment level. The problem which is involved in that is that during periods of high milk flow, we have a vacuum drop at the teat end. That means low vacuum. At low milk flow, we have no vacuum drop, so the vacuum can be rather too high. So the question is, what is an ideal vacuum level? And the answer is very easy. There is not an ideal vacuum level for the whole milking process. So high vacuum milking means fast milking, means short machine on time, but there is also a high impact on the teat tissue, with several consequences like long-term effects like hyperkeratosis and so on. Low vacuum is much more gentle, but is leading to slow milking, long machine on times. At the end, if the vacuum is really very low, also risk of liner slips. But still, even if the milking time is longer, the impact on the teat tissue is less, but it's very low in economy because the milking just takes a lot of time. So why is right vacuum setting a continuous matter of discussion? Since more than 100 years, we can say, since we have the same type of milking machines. So there are basically two vacuums involved in this double chamber milking unit. The pulsation chamber vacuum, this is the easiest one. It has only the task to cyclically open the liner. And the other vacuum inside the liner, where also the teat is, so the teat end vacuum, has a number of tasks. Stretch the teat and maintain the friction and seal between the teat and the liner. Close the liner, including massage, if atmospheric air in this pulsation chamber, suck the milk out of the teat when the liner is open, and transport the milk through the milk tubes. So what is the ideal vacuum? Because all these different tasks use vacuum. So that means high milk flow causes a reduction of vacuum. So there is an optimum level defined by ISO, so the International Society of Standard, which should be between 32 and 42 kilopascals at the teat end. And it seems that this is quite a good area of vacuum level to have a rather fast and also gentle milking. But of course, for the work performance, it's better to have the vacuum a bit higher than a bit lower. That means close to the 42 would be then the ideal vacuum level throughout milking. So if the vacuum is at a certain defined only one setting, is rather too high at low milk flow, rather too low at high milk flow. The optimal vacuum setting is a compromise between maximum performance and minimum impact on the teat. So as you can see in this picture here, the teat end vacuum without milk flow is the same as the vacuum in the pulsation chamber, is basically the same as the system vacuum. At one location here, at the evacuation of the pulsation chamber, the liner opens, then we get milk flow, and when the pulsation chamber is ventilated again with atmospheric air, the liner closes. And below here, below this vacuum levels where the opening and closing of the liner takes place, this is the vacuum which is needed for a full closure of the liner and also for the massage. And if it is more than necessary, then we get the so-called overpressure. If there is milk flow, the pulsation chamber vacuum is still the same, because the pulsation chamber vacuum is not influenced by milk flow. But the teat end vacuum is lower because there is a drop of vacuum because the milk needs to be transported. And the consequence is the opening and closure of the liner occurs at a much lower level of evacuation already of the pulsation chamber. And when it closes, there is much less vacuum left for the massage effect and for the full closure of the liner. So that means if the vacuum drop is too high and we have too little vacuum left at the end of the teat end, we get an inadequate closure of the liner and an inadequate massage. That means there must be more vacuum during the no milk flow period to have still sufficient vacuum at milk flow. Okay, so low teat end vacuum, means low intensity of suck at open liner and also a low intensity of massage. Therefore, the setting of the system must always be high enough to have still enough vacuum during high milk flow. Another important recognition, which was recently published in JDS, is when does the impact on the teat end really happen? And it is quite clear, either with ultrasound or with so-called cutimeters, which is a caliper, a spring-loaded caliper actually, which compresses the teat, which is ideal to measure the teat tissue thickness. You can see throughout milking, so before milking, after milk let down, after 2 minutes of milking, during the plateau phase, at the end of milking, there is not much of a change here in the tissue thickness, but if there is a few minutes of over milking on a specific teat, then the tissue thickness increases. And the same is the case here with ultrasound measurements. So the teat wall diameter can be measured with this type of ultrasound images. So towards the end of milking, and specifically during an over milking process, we get an increase of the thickness of the tissue, which is an indication of an increased load on the tissue. So the problem is the end of milking, when the milk flow decreases or even ceases completely. So what are the solutions to cover both problems? So a simple solution, at least to cover part of the problem, would be pre-stimulation to prevent at least a low milk flow period at the start of milking. This is first of all time consuming. And I have heard that pre-stimulation is not that familiar in Australia and New Zealand. It's more a European thing, what is done very carefully, but down under not so much. And the point is also, it's time consuming and it does not help very much at the end of milking. So at the end of milking, the milk flow will be low, and then we have this increased impact on the teat tissue. So what helps? Cluster detachment at a very high level. So there are studies now more recently published that show even up to 1 kilogram per minute milk flow. So that means really when the milk flow starts to decrease, detachment helps enormously to reduce the impact on the tissue. And there's obviously not much loss of milk long term, and there is also no increased risk for mastitis and so on, which could be assumed. So it's not a problem to remove the cluster quite early to avoid the time of low milk flow at the end of milking. And then there's another option to solve the problem with the question, what is the ideal vacuum? A milk flow dependent adjustment of the vacuum during milking. So because now in milking equipments, very often there is an automatic milk flow recording, a continuous milk flow recording, which is rather exact enough at least. The vacuum can be adjusted based on the signal of milk flow. That means a low vacuum at the start of end of milking during this period of low milk flow. And when the milk flow starts to be high, then to switch up the vacuum level to have a faster milking. And with this, I want to show you just a recent study, which we have performed here at the University of Bern. So there is a paper published in Journal of Dairy Science, not yet available. The print proofs were just sent last week, so I guess that in 2 or 3 weeks, the paper will be available online. 2 hypotheses. Hypothesis 1 is high vacuum and high detachment level, both will cause an increased milking performance. That means will shorten the machine on time, will increase the average milk flow. Secondly, vacuum reduction during low milk flow periods and a high detachment level will prevent an increased mechanical load that would be caused by the high vacuum. Okay, so we tried that out. Very short, the settings are a rather high vacuum, high system vacuum, 53 kilopascals, versus a low one or a regular one, 46 kilopascals. And both settings were used with or without an automatic vacuum reduction by 7 kilopascals during times of a milk flow which was less than 2 kilograms per minute. So all periods of the milking, less than 2 kilograms per minute. It means at the start and at the end of milking, there was a vacuum reduction 7 kilopascal lower than the full vacuum, the full system vacuum. And in addition, we have used 3 different detachment levels. So 0.2, 0.6, and 1.0 kilograms per minute. 0.2 is a bit the classical removal, so really close to 0. 0.6 is a more, let's say, average level of detachment, which is frequently used in the meantime. And 1.0 kilograms per minute is a rather high detachment level. So how does the figure look like of the vacuum at the teat end? We have 2 treatments here, high vacuum but no reduction. So HNR means no reduction, high vacuum, no reduction, compared to the same vacuum level with reduction at lower than 2 kilograms per minute. So you can already see here, without reduction, there is a very high increase of vacuum acting on the teat end up to 50 kilopascals. Then through the milk flow, there's a drop of vacuum, and then there's a lower vacuum during the plateau phase, about 45. And then when the milk flow starts to cease again, the vacuum increases. So we have again a 2 high vacuum at the end. With the reduction, it looks different. You see, we have 7 kilopascals left. So after attachment, we come up to 40 kilopascals. So not a problem. It's well in the range. Then because the milk flow starts slowly, we get a drop of vacuum here. At this point here, when this is actually the point, the upshift point, where the milk flow reaches 2 kilograms per minute. Then we have the shift up for 7 kilopascals, and from then on we have the same vacuum level than on this side here. So during the peak flow and plateau phase, the vacuum is not different, but at this time here, when the milk flow starts to decline again, then we have first an increase of the vacuum, and then we have the switch, downshift of vacuum, 7 kilopascals, and then we are much lower. So during this period, again, when the milk flow decreases, we have the switch to prevent this high vacuum, okay? So here is a table showing all these numbers. We have the same done with the lower vacuum setting, so the 46 kilopascal. This is certainly less interesting, but we see the same effect here. So again, this 7 kilopascal reduction. Important is the high vacuum here. So with the reduction, we start at an average in all experimental cows of about 37 kilopascals. Without reduction, we come up to 44 as a mean value. And then we have these shift levels. So we are quite low, 32 kilopascals, 39 kilopascals. And at peak flow, we come up to 37. So quite an ideal vacuum level, which is the same with or without the reduction during low flow. But then at the end of milking, at detachment, sorry, we have again a much lower vacuum if we have the vacuum reduction, and basically too high vacuum, as according to the ISO recommendation, too high vacuum if we don't use the reduction. So important now, the milking performance. Average flow, you can see these are the two treatments with a low vacuum, and these are the two treatments with a high vacuum. And I have to say, especially if the cluster detachment is very late, so at 200 grams, the vacuum, no vacuum reduction has the higher performance, okay? But still, with the vacuum reduction, but high vacuum, we have a higher milk flow than with the low vacuum. The higher we go with the detachment, up to 1 kilogram per minute, the less is the difference between the vacuum reduction at the start and the end of milking or no vacuum reduction. Always with the vacuum reduction, the performance is a bit less, but it's always higher than with the low vacuum. The same or the opposite we can see with the machine on time. So with the high vacuum, we have a shorter machine on time. If we include the vacuum reduction, then we have kind of a difference. So the machine on time is a bit longer, but still much lower than with the low vacuum. So there is really a gain of milking time. So what is the effect of this vacuum reduction? Do we really need it? And then you can see here, the answer is really yes, especially at the higher detachment levels. So most pronounced here at the 0.6, we can see that the cutimeter measurement, the tissue thickness, is really much less with the vacuum reduction compared to no vacuum reduction. This has a high value, and this means, of course, that the vacuum has a significant effect on the tissue thickness, but the vacuum reduction has, especially if we use the high vacuum, then we have less tissue thickness with the high vacuum. With the low vacuum, it does not matter. So they are quite similar, but of course, this is the setting with the less good milking performance. The detachment level, because it is so short, so the difference is so short, did not have an impact on the tissue thickness, just on the milking time then. Okay, so the same is visible with the ultrasound. So it's done like this, teat ultrasound in a water-filled cup to see the teat like this, and then the measurement of the teat walls is performed. So we see the highest teat wall diameter if we have a high vacuum use, but no vacuum reduction. With the vacuum reduction, we are much better off. So the high vacuum is okay, and even we could go higher than we have used in this experiment, but during the periods of low milk flow, it is important to have a vacuum reduction. So conclusions related to the study: high vacuum combined with high detachment level improves milking performance, and if the milking is performed at high vacuum, a vacuum reduction is important to prevent increased impact on the teat tissue. So this combination, high vacuum but lower vacuum during low milk flow, is ideal for fast and gentle milking, and is of course possible today with modern equipment to have an automated control of vacuum based on the milk flow. So I come very short to the second part of my talk. There's much more than only milking settings, milking machine settings that can be adjusted. There is a number of factors that can be just directly at the cow side analyzed in the milk as a type of a non-invasive surveillance of production and health. And just a few examples. So for mastitis control, somatic cell count equipment is available today, included mainly in automatic milking systems. I have to say all these measurements are also possible in conventional, but the industry in the moment offers them mainly for automatic milking systems. Lactate dehydrogenase is an enzyme that can be measured with a sensor. Cell damage indicator also for control of clinical mastitis. I will show later that the combination of somatic cell count and lactate dehydrogenase can even be an indicator on which type of pathogen is present. Okay, there is acute phase proteins, milk amyloid A, haptoglobin. They are mastitis indicators. Electrical conductivity is a very cheap indicator of mastitis, but not a very valuable one. But in combination with other parameters, it can be helpful. So reproduction can be controlled because there is progesterone also in the milk. So we can, automatic progesterone profiles can be recorded. This equipment is available already for automatic milking systems. Metabolism, urea. High urea means too much nitrogen relative to the available energy in the feed ration. So either too little energy or too much nitrogen. High ketone bodies. So it's possible also to measure beta-hydroxybutyrate and acetone in the milk. Always an indicator of a lack of, or indicator of lack of energy, mobilization of fat reserves, risk of ketosis. And newly, there is also studies going on about machine learning algorithms. For instance, a prediction of somatic cell count instead of the measurement of somatic cell count just by electrical conductivity and milk flow recordings. This seems to be the near future, these things to come. And just
Hi, Rupert,
a few examples.
Yeah, 2 minutes left, sorry, if that's okay.
I'm close to be finished. So maybe you have heard about the herd navigator. This is equipment sold by Delaval for automatic milking systems, which can measure progesterone, can measure LDH, lactate dehydrogenase, and beta-hydroxybutyrate. So short, I explained already what these measures are valuable for. Here is just an example of this frequent recording of progesterone. You can see here is cyclic activity, again a cycle, and here is pregnancy. And in between is the ideal time point for insemination. And finally, just a study which we have done in collaboration between the University of Sydney, that means Yanni Garcia's group and my group, to combine different parameters for mastitis detection. So this is a combination of somatic cell count and lactate dehydrogenase. And as you can see, they are not on one line here. So if cell count is high and also the LDH is high, it's mainly an indicator that gram-negative bacteria are causing the mastitis, so coliform bacteria, and it's different than for other bacteria. So each bacteria type has a different combination of somatic cell count and LDH. So at the end, if this work is still ongoing in a way, so if this can be really optimized, we can predict, we can say which type of bacteria is causing the mastitis, and then the treatment, of course, can be adjusted accordingly. My final slide. So the scientific basis of novel milking-related precision dairy farming tools are increasingly developed. It is the role now of the industry to make suitable products, affordable products for the dairy industry. Thank you for listening, and if there are any questions, I'm ready to answer them. Thank you.
Thank you very much, Rupert, for your presentation. I think it's been a great insight into a topic that has been around for some time, but obviously there's been a lot of research recently, and you've highlighted some of them. There's two questions that came through that I had to filter given time. One is, do you think there's going to be more advancement in automatic milking systems given the quarter milking of cows, or more sensors included in conventional milking?
Of course, many things is just to say it's easier in automatic milking. Like quarter milking is so easy because it's already quarter milk. It's much more complicated in conventional. I believe that the industry should put more effort also in the conventional milking, because not in every country, not in every circumstances, automatic milking is the ideal way of milking. So because all focus during the recent years was put on the automatic milking, maybe the conventional milking part has remained a bit behind for this period. They need to catch up, I have to say. Maybe the farmers, the dairy industry themselves, they should push the milking machine companies to come up with new developments also for the conventional systems. I think there's a lot would be possible easily also in conventional.
Excellent. And the second question is, do you think there is potential to pair up sensors that measure things in milk with cows' behavior to detect pathogens and diseases?
This may be possible, yes. I mean, today, as I just shortly mentioned, this machine learning algorithm things, what is going on, I think there is a lot, just behavioral indicators can play a role. I have to say, my group, I'm a physiologist, so I am more stuck really to the things that can be measured in liquid, like blood or milk. But I know that also behavioral studies, like I know heat stress indicators, for instance, are very much popular now, just based on behavioral markers in a way. So I think there is potential, absolutely.
Excellent. Well, Rupert, thank you very much for your presentation today. It's been a pleasure having you here with us from Europe, and I know it's late over there. So thank you for your time, and hope to see you again, hopefully here in Australia.
I hope so as well. Thank you very much. Thanks,
no worries.
all of you, for listening.